on natural language processing. My name is Reda Bouadjenek, and I'm a lecturer of applied AI at the School of IT. So today we'll talk about transformers, which is the current cutting-edge technology for sequence modeling and especially used for natural language processing. And if you are interested in collaborating or working on the NLP topic, please let me know. You can email me. So, when you hear about the term transformer, you may think about, everyone think about this movie, right? Transformers movie. But when an NLP person or a deep learning person hears about transformers, he thinks about this encoder-decoder architecture, and that I'm going to present today. Okay, so my point was initially to present BERT, and BERT will be the third lecture for this NLP series. And to understand BERT, this Chris McCormick, who is a YouTuber putting a lot of videos on deep learning, has proposed this mountain, this BERT mountain, that you need to climb if you want to understand BERT and the BERT mechanism. So BERT makes this claim that all you need is attention, and you don't really need this recurrent information that goes over the entire sequence, right? And this is really the idea behind BERT and the transformers. So BERT relays on transformers that I'm discussing today. So a little bit background. I think it's important to know the basic concept behind recurrent neural networks, LSTM, BLSTM, the idea behind encoder-decoder, attention, which is very important mechanism in natural language processing, and then today we will talk about transformers. So this is the outline of my presentation. I will start briefly talking about some background, NLP in general, and then sequence modeling. Then I will present LSTM, the idea behind LSTM, and say why LSTM are not good enough anymore. And at the end, I will present transformers, how they work and why they work, all the mechanism behind the transformers. So let's start with the first part, NLP on background on NLP. So, I will go quickly on this part. So, in NLP, the task is really about defining a function that allows you to map a document, a sequence of words or a paragraph or even an entire document or a sentence to some label. It can be classification or regression, but an example is to do, spam classification, right? You have an email and you want to discover if this email is a spam or is not spam. So the problem with sequence is the fact that I'm not aware about any linear algebra that allows you to map a variable size vector to a real value or binary value or discrete value, right? It doesn't exist, right? So in linear algebra, usually what you have to map needs to be like a fixed size vector, right, to real value. Okay. So to deal with this problem, the first idea that was widely used, especially with information retrieval, is the idea of bag of words. And here is the idea of bag of words. A document here is represented as a vector. Each dimension of that vector is a term, a word, right? So it's going to be one dimension per word. The vector size is the vocabulary size, right? So the vocabulary size is the size of your vector. So in English, you may have, let's say, 100K words, which means your vector will be 100K here, right? This is the size of your vector. So now, how do you weight each entry in your vector? So if in your document this word appears in the document, then you put some value here. And the value can be, the frequency, the log frequency, the TF-IDF, or it can even be a Boolean weighting schema like here, right? Number one, it means it appears. If it's 0, it means this word doesn't appear. Like, for example, this document is, I am a student, right? It's represented in this Victorian space like this. So, of course, the vector, or all vectors, are going to be sparse vectors because most of the entries are zeros, and that's obvious. Okay, so the bag of word makes a strong assumption, which is the fact that, the sequence or the sequence order is not important. It's not taken into account, right? And that's why, if you take these two sentences, right? John likes Marie, and the sentence Mary likes John, in this vector representation, it's exactly the same representation, even though the semantic is completely different. But in the word, in the bag of word representation, the vectors are exactly the same. So you won't be able to distinguish this sentence from this sentence, and that's a problem, right? It's a problem. It may work well. It works well in practice in many information retrieval tasks, but it doesn't work well for natural language processing tasks. Let's see an example. So if you take the task of sentiment analysis and you have these two sentences, first one is, no, there are good movies on Netflix, right? And this is clearly a positive sentence, right? That's a positive sentiment. So if I take this no here and just move it here, right? And just move this no, it becomes this sentence, there are no good movies on Netflix. And this is clearly a negative sentence, right? And that's why for many NLP tasks, the sequence is an important component, right? You need to keep the sequence, the sequence of words. So still, you know, in the bag of word model, you still be able, you can represent in fact, or you can somehow, there's a trick that allows you to, you know, take into account the order of words, and the approach is called the n-gram, right? Previously, what we used was the 1 gram, right? 1 gram, right? Where basically each entry of your vector is going to be one word, but in the n-gram, each entry of your vector, it's going to be a combination of n words. So for example, if you take 2 grams, right? So this will be an entry in your vector. This will be an entry of your vector. This will be an entry in the vector, etc., etc., etc. And this is the 2 grams. So let's do some math, right? Dimensionality grows exponentially. So if you take n grams, the size of your vector will be v to the power of n, right? And the example is if you take 3 grams with English, which is 10 to the power of 5, 100k words, right? So the vector size will be the size of your, 3 grams, so basically 10 to the power of 15, which is 1 million of billion, and that's too expensive. In practice, it just doesn't work, right? And that's an issue. So that was the bag of word approach, and to deal with this problem, recurrent neural network have been proposed. And the idea behind recurrent neural network is just, you know, trying to compute a function that allows you, define a function that allows you to map this sequence, right, into a value y, right? And the idea to solve this problem with recurrent neural network is just to define, you know, a for loop function, right? Basically, you go from all your tokens in your sequence, like from token number 0 to token n, right? It's a loop. And what you compute some information h here, h subscript a plus 1, which is a function of the previous stuff you have computed with respect to the current input, right? And that's the representation of recurrent neural network. So basically, you know, you have your function here, right? You have some information coming from the previous timestamp and the information coming from the current timestamp, right? So for example, the token x0, right? You pass some information. This is the information you pass, which is h1, right? Now you pass x1, and then you compute x2, right? And this is always the same function, right? Now you pass x3, you compute h3, x2, and you keep doing that, right? And this is recurrent. That's why it's recurrent neural network, right? You have this recurrent loop here. So they are, of course, usually represented using this enrolled representation. But just keep in your mind that the information or the weights that are computed here are, of course, shared here, right? It's exactly the same weights. Okay, so let's talk a little bit about a problem that recurrent neural network have, which is what we call vanishing and exploding gradient, especially if the sequence is very, very long. So just some definition. Okay, so again, h is a function of is calculated as a function that takes as input like the previous timestamp hi and the current information, the current token xi, right? And that's the computation that is done. Basically, you have two matrices, two weight matrices, right? The matrix W and the matrix Z, and it's just a matrix multiplication, right? This current token, the current input token, is multiplied by the matrix W plus the previous information, right? Multiplied by this matrix Z. You sum, and that's how you can compute your output for the current timestamp. Okay, so just some math. This is how you can compute H3, right? It's going to be, it's a recurrent function, so it's H of 0, 0, H of blah, 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 blah. You can unroll it, that's H of n, right? It's again a recurrent function, right? And if you unroll it, that's exactly what you get, right? H of n is equal to this, like W multiplied by xn minus 1, ZW multiplied by this, etc., etc., etc. What you can notice is this. Right? This matrix Zn is multiplied n times. And that's a problem. Right? You're multiplying a matrix n times. That's an issue, especially if n is very, very large. So just think a little bit. If you take a number that is a little bit lower than 1, like for example, 0.9, sorry, and you raise it to the power of 100, like, it quickly becomes a very small number, almost equal to 0, right? Similarly, if you take a number that is a little bit slightly higher than 1, right, you raise it to the power of 100, it becomes quickly very, very giant high number, right, a giant number. So this is if you raise it to the power of 200, right, it's almost 0. This if you raise it to the power of 200, this is really, really a huge number. So think that you have a matrix Z that you are multiplying multiple times. For sure, you will end up with this, not a number, or some values are just equal to 0. That's an issue, right? And this issue is called, in this case, vanishing gradient, and in this case, exploding gradient. Right? You're losing information because you are multiplying a lot of, it's a numerical issue. So to deal with this problem, LSTM, they have been proposed to solve this problem and LSTM stands for long short-term memory, right? Okay, so LSTM is a technology that has been proposed in 1997 by two German, I think, researchers. The idea is the following, instead of keeping just one single signal, is to have two signals, right? This signal here is called a long-term memory, right? It takes like really, it can remember information coming from really early tokens seen in the sequence, right? You really can capture some information coming really far in your sequence. This is the long-term memory. And you have some short-term memory here that is, of course, taking information from the previous, from the previous timestamp and some information coming from the new token, right? And you have this idea here to compute your long-term memory based on these gates, like the forget gate and the update gate, right? So you just each time you see a new token, you just update or forget some information from the previous, from the previous tokens, and that's the basic idea. So this is what you get if you put them all together. Like it's a long sequence, right? You can imagine this as your token x0, and this may be your token xn, right? And you have some tokens here. And what you can observe here is the fact that you have really like this long-term memory going all the way down, right? All the way down here. And as you can see, it's always, forgetting slightly some information or updating slightly some information through these gates, right? So the idea behind LSTM is really that at this timestamp here, the model is able to remember precisely some information that is coming from this token. So this is the idea behind LSTM, is really to carry these two signals, the long-term signal, right? Long-term memory signal and short-term memory signals, right? That's what you have here. Okay, so the problem with LSTM, they are limited. They have some limitations. They are difficult to train, right? Because it's a recurrent neural network. You have a lot of information to update, a lot of information to compute. They are difficult and painful to train. You will end up with very long gradient paths, right? LSTM on 100 word document has gradient of 100 layer network. Now, that's a huge, very, very deep neural network. And moreover, you have this issue that, transfer learning never really worked on LSTM. So there are, I know that some researchers that try to release like pre-trained LSTM for, trained on some tasks like language modeling, but it didn't really work. It didn't work, right? These are the limitations. And, okay, you need specific labeled data set for every task, but anyway. Okay, so that was LSTM, and now transformers. And transformers is really, the next big thing for sequence modeling, right? They are here to replace long short-term memory, LSTM. And the idea behind transformers, the claim behind transformers is really that, at the end of the day, let me just go back maybe here. Yeah, you just go back here. So you can notice here, in sequence modeling, like specifically in this LSTM or recurrent neural network in general, you can't process this token, the token xn, before processing x0 or x1, right? You have the sequence. You can't process xn before processing this one, and et cetera, et cetera. You have to process them in sequence, right? Now that's the issue. And, it doesn't allow you to have a proper parallelization of the computation done in these recurrent neural nets. So this is the idea behind transformers. The claim is that, in fact, you do not need the recurrence. All you need is the attention part. Let's see how it works. So this is really the next big idea. It's really, for me, the cutting edge technology for sequence modeling. So the idea was published in late 2017, December 2017. The paper's title is "Attention is All You Need." It's one of the highest cited papers in natural language processing. It's really a highly cited paper. So if you look at the paper, that's the schema that is given for transformers. It seems to be complicated, right? A lot of stuff are going on here, but so first, what you can note, it's just, please put in your mind that it's an encoder-decoder architecture transformers, right? So this part here is the encoder part, and this part here is the decoder. Okay, so this is the information that is given from the encoder to the decoder. Okay, so second thing to notice is this n time. So this is a single encoder, right? And you have multiple of them stacked on each other. So basically you have this encoder. Okay. So encoder 1 stacked over encoder 0, encoder 2, encoder 3, etc. You have n encoders that are stacked on each other, right? So this is the input. That's why you have this n times. And on the other hand, for the decoder, you have exactly the same architecture, right? You have n decoders stacked on each other. Okay, let's see. Yeah, that's the that's the transformers, right? You have in the paper they described an architecture based on 6 encoders stacked on each other. Okay, and then the last encoder passes its output to all the decoders that are stacked on each other. Okay, so let's see what you have inside each encoder. Okay, each encoder here. Each encoder does 2 things. It does this, what we call self-attention, or specifically multi-head self-attention. And then you have a regular feed-forward neural network. The encoder is able to process in parallel all the tokens. All tokens are processed in parallel. It's also the case for the feed-forward neural network, right? They are processed so these are completely independent from each other, right? It's a regular feed-forward neural network. And the encoder, of course, is able to process the input in parallel, right? It's not a sequence. It doesn't need to process the word thing before processing the word machines. That's the idea. So if you have questions, just please feel free to stop me. Okay. Yeah. So let's see. That's our architecture. In this talk, I will only focus on the encoder part, but you can imagine that the decoder part is exactly the same, right? It behaves exactly in the same way. Okay, that's the encoder. And again, as you can see, you have two things. You have your multi-head self-attention, which is this, with this normalization layer, right? And then you have this feed-forward neural network with, again, normalization layer, right? And you have these residual connections here. In the encoder, okay, so at the beginning, really at the first encoder, let me just go back here. Yeah, it's clear. So at the beginning here, before your first encoder starts processing the sequence, you have what we call here a positional encoding layer. So this positional encoding layer is basically a layer that will inject some information into each vector representing each token in your sequence, right? So for example, you have the word je, right, represented as a vector, what we discussed during the previous lecture on word embeddings, right? So je is represented as vector, and this vector you add, some position information, another vector. You just sum them. So you inject some information that tells to the model what is the position of this token in your sequence. Okay, so this is what you see here. Input embedding or positional encoding, right? You basically just inject some positional information to each token, such that the model knows what is the position of each token. Okay, so you have, again, three things. The first thing is your multi-head self-attention. Then you have the positional encoding, and then you have your feed-forward neural network, right? And it's of course, the token is processed this way. Okay, so for this part here, right, the multi-head attention, two things are done. You have what we call the self-attention that is computed, and the second thing is the multi-head self-attention. Let's discuss them in details. So self-attention, it's a mechanism that basically, makes a kind of, all-to-all comparison. Okay, so each layer is an n to the power of 2 for sequence of length n self-attention. What does it mean? It means that if this is my input sequence, these are my tokens, right? The self-attention will, for each token, try to compute what's the relationship between this token and all other tokens in my sequence, right? And this is what's called self-attention. It's really like the sequence itself, attention. It's the sequence with itself, really trying to understand the relationship between each token and the other tokens in the sequence. And that's the self-attention mechanism. So basically, you do this all-to-all comparison. So what does it tell you? It tells you a lot of information. Like, for example, it can tell you, like the semantic relationship between words. For example, when the word law here, or no, it's is a good example, right? When you say it's in this sentence, it clearly refers to law. The model is able to extract this information, right? And that's why you try basically to make, or understand what's the relationship between the tokens and each token in your sequence, right? Or maybe, I don't know, like the word opinion is related to my, I don't know, like never related to never, like, law is related to the, etc., etc., etc. Basically, really, the model tries to understand what is the structure of your sentence or your input paragraph. That's called self-attention mechanism. So in practice, how does it work? For each token in your input sequence, you have two things, or in fact, you have three things. You have what we call a query for each token. You have a key, and you have a value. So to compute these self-attentions, you first have to compute scores. And these are called relevance scores. So the relevance score is simple. If you want to compute the relevance score between the token making and the token difficult, right? You take the query vector representing making, right, index 17, with the key vector representing the token difficult with the index 24, and you just make a multiplication. And this gives you like really the relevance score of difficult with respect to making. This is the first thing you do. You compute this relevance score for each token. And again, it's an all-to-all comparison. So now the attention mechanism, once you compute this relevance score, okay, you have for each token also a value. Basically, if I come back here, right, I have a value, a query, and a key vector for each token, right? I compute my score, which is a scalar, right? And if I want to, compute how difficult is contributing to the word making, I take the vector value representing difficult, and I multiply it by the score that I just computed. Does it make sense, guys? I hope it makes sense. If it doesn't make sense, just please stop me. So just keep in your mind that the first thing to do is really to compute the score, the relevance score between each entry in your token and the corresponding token for which you want to compute the relevance score, right? And then you basically, in this case, take the vector that represent, the vector value that represent the token difficult, and you multiply it by the score that you just computed. And plus, you do it for all other tokens in your sequence to compute the final output vector for making. So at the end of the day, the output here for making is going to be the score between, let's say, it, right, and making, of course, multiplied by the vector of it plus the score of is with making, right, is and making multiplied by the vector of is plus etc, etc, etc. And this, what you obtain, is the output vector for the word making. This is really the attention mechanism here, the self-attention mechanism. So once you do that, right, you will end up for the word, for our word making, you will end up with a vector. On that vector, you apply softmax. Right. Okay. Okay. So that's for the self-attention mechanism. This is in pseudo-code. I think, I believe that it's easier. This really, I think, is easier to understand in pseudo-code, and that's why I put this pseudo-code here. So, if you want to compute this self-attention mechanism, right, you have your entire sequence as input. This is your sequence as input. So for each token in your sequence, that's your for loop here, you compute a query, a key, and a value. So you have some weighting matrices here, right? You have these weighting matrices, and you make a multiplication, right? You make a multiplication with your input. You compute your query, your key, and value vector for each token, right? So this is why you have this index I. Okay, next step. Again, you loop over all the sequence. You pick the query for the current token, right? You keep its query vector, right? You do a nested loop here to compute your relevance. So basically, for each token, right, you take its key vector, which you multiply by the query vector of the current processed token. You compute your relevance scalar. So just please put in your mind that relevance is a vector here, right? So now you computed your relevance scores, right, for this token, for the current token you are processing. And the next step is just by applying softmax function over the relevance vector, right? And you will have another vector which is normalized using a softmax function. So now let's compute briefly our output. So the output is going to be a vector per each token. So each token here, you will output a vector, right? So you initialize it with 0 vector. Okay. So again, a nested loop, you iterate over all your tokens in your sequence, in your input sequence, right? And each time you just multiply the value of the current token with its corresponding relevance score, and you add to the output vector. It's a sum. And that's it. It's easy as this, right? And at the end, you will output the final matrix. So this is a matrix, right? Where, okay, your matrix here, you have all the tokens, right? The size of your input sequence. And here is the size of the hidden vector, right? The hidden vector may be 512 or 256 or whatever. Okay, so yes, relevance scores are interpretable. You can interpret these relevance scores, right? So now, what's the multi-head attention mechanism? You know, basically, instead of doing this only one time, you can do it multiple times. And the basic assumption is that, you know, each time you are capturing some relationship between the tokens. Okay, so it's really clever idea, important innovation. It's not hard to understand, right? It's just, you know, you do it each time. And in the paper, they propose to do it 8 times with, of course, different QKV matrices, and let the network really learn, you know, different semantic meanings of the attention mechanism. So you may understand some, you know, or learn some relationships that are related to the grammar, relationships that are related to the vocabulary, to the semantic, to the conjugation, etc., etc., etc. So each time you learn something, you let the model to learn something related to your sequence. It's really a flexible mechanism for sequence processing. I really like it. I feel really, I like it. For me, it's really a clever idea. So at the end, for each token, of course, now you will end up with, you know, 8 vectors, right? 8 vectors for each token. And now the idea is just to concatenate the 8 tokens, right? Apply a linear layer, and you get 1 vector. It's as easy as this. I hope it makes sense, guys. If it doesn't, just please stop me. Okay, so we discussed this mechanism. Now let's just briefly discuss a little bit this positional encoding, this positional encoding layer. So I briefly talked a little bit about it earlier. So, you know, if you don't use this, you know, the attention is just a bag of words model, right? Because you don't have, if you just use the attention mechanism, you know, if you just use it, you do not, you know, you do not keep the information related to the sequence of words, right? And that's an issue. And, you know, the authors of this paper, the transformers paper, is to, you know, deal with this problem by adding this input layer. Basically, you know, a word embedding and a positional embedding, right? Injecting some information related to the position of each token to the embedding layer, to the embedding of each word. So position can be either learned or fixed. So that's what they claim in the paper. Fixed allows extrapolating to longer sequences. Okay, anyway. So again, this is the idea, right? You have the embeddings that corresponds to each input token. This is what we discussed during the previous talk, the first lecture, right? It's an embedding, right? A vector representing the semantic of your word, for which you add positional information, right? And then that's the new vector that you will give as an input to your transformer, to the first encoder. Right? You do that for all tokens and let the model to understand what's the position of each word in your sequence. This is really the big idea behind the paper here. Okay, so it's, yeah. So the idea of this positional encoding is based on some, Fourier theory, right? But this is an example, right? You basically have to inject this vector if it's four-dimensional vector as an input, right? You have 4 dimensions here. You may have to inject this vector here, this vector here, this vector here, and that's really the model to understand or to learn the position of each token in the sequence based on what you have injected in the embeddings. Okay, so let's see it all together and the encoder in action, right? So again, your encoder is receiving each token. It processes the tokens again in parallel, right? It doesn't need to process them by sequence, and that's why it's super fast. So as you can see here, they go through the first encoder, they go through the second encoder, they are outputted here, and then they are given as input to each of the decoders. But you can notice something. Let me see. Okay, so your encoder is outputting here the first token. So now if you connect it to the decoder, this is decoder, you can notice something here interesting, which is the fact that for the decoder, you have to decode token by token. You cannot decode the entire sequence in parallel. That may be a limitation, right? That may be a limitation. But again, so when you decode each token that you output here, you will put it as an input for the next time step, right? And then you process the second one as an input here. Next, the third one goes as an input here, etc., etc., etc. Until you generate. Okay, so this is the fourth one, which goes as an input here, until you generate the end of sequence token and you stop. Okay, so why transformers are awesome? Because it, this all-to-all comparisons, they can be done fully in parallel, right? And that's really an important innovation because, we have GPUs, they change the game for compute, right? And square, but extra parallel operation can be free. Recurrent neural networks, LSTM, there is an error here, sorry. LSTM. Yeah, must be computed in sequence per token. That's the major limitation for recurrent neural networks, LSTM and recurrent neural networks. So in terms of performance, the paper, estimates the quality or the performance of transformers on this task of language translation. And usually in language translation, the performance is estimated using this what we call BLEU score. Okay, so the BLEU score is a score that is used to, estimate the quality of a translation of a sequence generated. It's not bounded, okay, and the highest is the BLEU score, the better is your algorithm, okay. So it's compared with multiple algorithms against multiple algorithms, and two versions of transformers of the architecture are compared. You have the base model and the big model. And as you can see, it's compared on 2 different tasks, the English to German translation and the English to French translation, 2 tasks. And as you can see, that for the BLEU score, it's almost achieving the highest score, right? Always achieving the highest score with respect to these very complex architectures. So now, in terms of training cost, they use this FLOP, which is the cost of number of iterations that is performed by each algorithm. As you can see, it's much cheaper, especially the base one. Right? It's much cheaper, much cheaper compared to all the competitors. They are all raised to the power of 20 and 21. Okay, so this is just if you're interested. This is the literature. This is the original paper, and these are really some useful references. So if you want to get my slides, they're available on my website. Just please feel free, go there and download them. So thank you very much. If you have questions, I will be more than happy to answer them.
Any question? Okay, apparently nothing. Thank you very much, Reda,
So
for
let me just sorry. Let me just say something.
Go ahead.
Sorry. Just to tell or to make the connection with the next presentation, the third lecture, which is about BERT. And BERT is simply, let me just go back to the architecture here. So what is BERT? BERT is simply this part. So BERT is this. This is BERT. So BERT is basically just some encoders that are stacked on each other, making a lot of and several self-attention computations, right, and trying to extract, relationships between tokens, between input tokens, right? That's BERT. And BERT is a pre-trained model that is pre-trained on, some specific tasks, on two tasks related to language modeling and also classification task. So it's pre-trained model that basically tries to, understand and capture some low-level relationships between tokens, between your input tokens, right? And then BERT, okay, so if you use BERT to do any NLP task, so BERT will output for each input token a vector, right? And these vectors are what you will use to make your pre-trained, to make your pre-training. Sorry. So this is the pre-training part and the fine-tuning part. So for example, if you want to make some classification, you just have to maybe pick this vector here, put it into the classification layer that will output for you a classification label like 0 or 1. I will describe it next week. I think it's next week, right, Asaf?
No, it's going to be in 2 weeks.
Okay.
Essentially, it's going to be 11th of June. But that's a great incentive to prepare people to think about BERT till next time.
Yeah, so that's BERT. BERT is just simply, the encoders that are stacked on each other. That's BERT.
Yep.
Okay.
Fantastic.
So if no questions, we are good to go.
Let me see. So there is a message. So Ming.
I can't read them. I don't know why.
Can you see the messages, Reda?
Oh, yeah. Thank you, Reda. I'm also working on NLP. Yeah, current pre-trained plus fine-tuning paradigm is very expensive. So far, researchers like us who don't have a huge amount of GPUs, what kind of research direction do? So I'm not sure what kind of GPU resources we do have here at Deakin, but I think you can apply for resources at Nectar. Maybe check with Nectar. That's the first thing to do. I think they have some GPU resources that you can get. So yes, it's very expensive. It's fine. Yeah, so really it depends. Okay, let me tell you. So can you see my slides, guys?
Yep.
Yeah. Okay. I will put it here. So, when you apply your fine-tuning on BERT, so let's suppose this is BERT, right? And you input your tokens to BERT, right? Maybe the phrase, I don't know, I am happy, right? And then end of token, end of sentence, right? And here, I mean, if you know BERT, you know what I'm talking about. So here you have the CLS token, right? That is input here. So for each token you input, you have a vector that is outputted by BERT. So if you want to use or classify this sentence using BERT, you take this vector, and then you apply a classification layer, right? That will output for you the classification label, right? So you have two choices here in BERT. You can either freeze this the entire BERT. You can freeze it and just, make or fine tuning on this classification layer, and this is cheap. Or of course, if you try or you want to, make fine tuning over the entire BERT, this case it's gonna be expensive because in BERT base, if I remember correctly, you have roughly 130 million parameters in BERT itself. It's a huge amount of parameters. So in BERT base, so this is for BERT base. I think for BERT, how do they call it? I don't remember. Like the big BERT. Yeah, big BERT. Like, big BERT. Yeah, I think you have 3,050,000 parameters or something like that. But let's stick with this one. So this one will output for you here a vector, a hidden vector of 756, I think. That's the size of the output vector. So if you are doing a binary classification, the size of this here is going to be 756 by 1 matrix, right? You have only 756 parameters to learn. If you only choose to apply, to fine-tune only this part here, to tune only this part here, it's going to be super, super cheap because you are only back propagating over this layer here. You have only 756 weights to find, right? But if you try to, fine-tune the entire BERT, right, this is going to be expensive because you have 130 million parameters to update. Now I hope it answers your question. Let me see. I can't see. Okay, cool. Thank you, Ming.
All right, I'm going to stop recording.
Okay, cool.
And
thank you very much, Asif.
No worries. We will see you in 2 weeks again.
Okay, cool. Thank you, guys. And yeah, I hope to see you next week.
Sure. Bye for now.
Bye.